So lesson 7 is going to look at doing transformations with these cosine, sine, and tangent functions. But before we get into talking about the transformations, we need to make sure that we have a firm understanding of what the characteristics are of these graphs. So if I start off with my sine graph, y equals sine x. If I'm just looking at one period, one rotation, it's going to go from 0 to 360 degrees or 2 pi. Cos and sine both have a period of 2 pi. Sine starts at 0 and makes this kind of a curve. Halfway through is the 180 or the pi mark. Then I've got these max that are also halfway, 90 degrees or pi over 2, 270 degrees or 3 pi over 2. A max of 1 and a min of -1. That's my sine graph. My cos graph, if I put it on the same grid, starts at 1 and ends at 1. Halfway in between, it's at -1. And then the halfway points is where it goes through the x-axis. So the halfway between 0 and 180 are at 90 degrees. It's going through and it's going back up. So the cos graph and the sine graph are very much the same. In fact, if I took my cos graph and slid it over, it would actually match up to the sine graph. It just starts at a different point. The tan graph, however, does not. First of all, for the tan graph, it is probably easier to see both sides of the graph. The other thing the tan has is, first of all, the period is only 180 degrees. And then I've got all of these asymptotes. So where are the asymptotes on a tan graph?
At 90 and 270. And then negative 90 and negative 270.
So if I had to write that as a fraction, as a function, it would be starting with 90 and then adding multiples of 180. That would be where I'd find all of the asymptotes. So that's what I want to put in first, is I want to put these asymptotes in. So 270, 90, -90, -270. And then I have my -180, my +180. And then the tan function basically gets this repeating look to it. If I'm starting from 0 to 360, what I see is this, this, and this. So this point here would be at 360. So I have x-intercepts at 0, 180, 360, and on, or multiples of 180. If I go backwards, looks like this. Oops, didn't do that very well, like that. And then this one would go up like that from -360. But really, it's this type of a pattern. So I end up having this point of inflection that happens here. Tan does not have a maximum or a minimum value. It extends up indefinitely. And that was seen in that class assignment that you did, where you had to calculate what was tan 90 degrees. Or sorry, you can't calculate tan 90, but if you calculated tan 80 and then 85 and then like 89 and 89.5, you would see that the numbers just kept getting higher and higher. If I was at 90.1, it would be very low numbers. Large low numbers, but still lower numbers. Okay? Does that help to kind of clarify what you should be getting for your graphs? Okay. So remember when I said in chapter 2, when we did the transformations, that this chapter is going to come back all the time? it's coming back again. So just like we did with the rational functions and with my quadratics, we did this when we were looking at the exponential and the logarithmic functions. We're going to look at transformations. What does adding an A value or a B value or a C or a D do to the graph of cos x? So if we go back to our replacements and we go back to some of our general understandings, we should be fine. So what we're going to look at in this lesson is what A and B do to the graph. So if we use the knowledge gained from that transformation unit that we did way back in September, if I have the graph of y equals sine x and I now compare it to the graph of y equals 2 sine x, what replacement did I make to this graph? I replaced y with a 1/2 y, because that 2 was actually on the other side. So if I replace y with a 1/2 y, what transformation am I making?
A vertical stretch by a factor of 2 about the x-axis.
So vertical stretch about the x-axis by a factor of 2. Okay? Do the next 3. Okay, so what is my replacement for number 2?
X is replaced with 2x.
And what does that do to the graph?
Horizontal stretch above the y-axis by a factor of 1.
So horizontal stretch above the y-axis by a factor of 1/2, because it's always the reciprocal of what my replacement is. So what happens in 3? What's my replacement?
Y with a 1/3 y, and then a y with a negative y.
So y with a 1/3 y and y with a negative y. What does that do to the graph?
It's a vertical stretch by a factor of 3 above the x-axis.
Okay?
And then it's a reflection in the x-axis.
Reflection in the x-axis. And finally with 4, what's my replacement? Hannah? And what does that do to the graph? What's the factor? 1/3. Doesn't matter if I do the reflection before or after the stretch.
Oh no.
No, it doesn't matter. It's only when I translate, and actually it's only if I translate horizontally. If I was translating vertically, I could do the translation first and then the stretch and the reflect. Typically, we save our translations for the end, always, just to make it consistent. Okay? Which of these values, the vertical stretches or the horizontal stretches, are going to impact the amplitude of my graph? Remember what amplitude was?
It's like minimum and max.
The minimum and the max. So what's going to affect the min and the max?
Vertical stretches.
The vertical stretches. So that's 1 and 3. Which examples are going to affect the period of the graph? What's the period?
The time it takes for the graph to repeat itself.
So the time it takes to repeat itself. So what's going to impact the period?
Horizontal stretches.
A horizontal stretch. So that's 2 and 4. Okay? So now what I want you to do is use, if you need to, use a graphing calculator until maybe you start to see a pattern. And I want you to look at all of these equations, except the last one, because you don't have any values. and determine what the amplitude and the period are of all of these graphs. And if you start to see a pattern, it might make the chart go faster. Okay, so what is the amplitude of sine x? 1. And the period?
360 degrees.
What about 2 sine x? What's the amplitude?
2.
The period?
360.
What about sine 2x?
1 is the amplitude. And 180 degrees.
What about negative 3 sine x?
Someone else can answer.
The amplitude was 3,
Period?
360 degrees.
What about sine negative 3x?
Amplitude was 1. The period was 120 degrees.
Are we starting to see a pattern? What is the amplitude? Where can I find the amplitude in the equation?
In front of sine.
In front of sine. Is that a value? Okay. What about when I have a negative 3? Does that affect the amplitude?
No, because it just reflects the graph.
Amplitude is an absolute value number. It's always going to be positive because it's measuring distance from the center to the graph to the maximum, or it's half of the minimum to the maximum. So it's always a positive distance. What about the periods? What can I use to help me determine the period?
Can use the replacement with x or multiply 360 by the factor of replacement.
Okay, so the replacement here was a 1/2. Half of 180, or sorry, half of 360 is 180. This one was a replacement of 1/3. A third of 360 is 120. Or 360 divided by 2, 360 divided by 3. Either one works. So with that, 5 sine 4x, what should the amplitude be? 5. And then what should the period be?
90.
And I should be able to get 90 by going 360 divided by 4, or replacement 1/4 of 360. So then my amplitude for the last one, 1/3 sine 1/2 x.
1/3 is the amplitude.
And what is the period?
720 degrees.
Because my replacement would be 2. Or sorry, my replacement is 2, which gives me a stretch. Let me say that again. Replacement is 1/2, which gives me a factor of 2. Or if I went 360 divided by 1/2, I would get my 720. So if instead I just had A and B, so A sine BX, what is the amplitude going to be? The amplitude will be whatever the value of A is, and what is the period going to be?
360
So 360 divided by B. What would happen if I changed all these graphs to cos graphs? Would I find the same pattern? So what's the amplitude of cos? Normally. 1. What's the period of cos?
360.
360. So if I replace cos x with a 2 cos x, do you think I'm going to get an amplitude of 2? Yeah. If I replace it with a cos 2x, am I going to get a period of 180? Yes. What would happen if I decided to go after tan, though? How would this change with tan? First of all, does tan have an amplitude? It doesn't really have an amplitude. I would still get these stretches, but I wouldn't actually record an amplitude with tan. What would happen with the period? Instead of dividing 360 by B, what would I be dividing?
180.
180, because tan's period is 180. Okay? So the next page basically, in a sense, summarizes this. If we change the parameter A on the graphs of A sine x and y equals A cos x, I get a vertical stretch. When the value of A is greater than 0, I get a vertical stretch of a factor of A about the x-axis. When A is less than 0, I have that reflection worked into it. So I also have a stretch, but then I have a reflection. And we talked earlier about the order doesn't matter. Okay? If I change the parameter, changing the parameter A also results in a vertical stretch. It's just not recorded as an amplitude. Still a vertical stretch, it's just not, it's harder to see in a tan graph because it extends indefinitely in my y values. Changing the parameter b on the graphs of sine bx, cos bx, and tan bx gives me a horizontal stretch. When b is greater than 0, I get a factor of 1 over b. When it's less than 0, I get that reflection in the y-axis and a horizontal stretch. So these two charts down here are useful in that it helps to remember how do I calculate amplitude, max minus min divided by 2. How do I figure out the period 360 divided by the value of b, or if I'm in radian measure, 2 pi divided by b. The lines on either side is a symbol for what?
Absolute value.
Absolute value. So it means that if b is a negative 3, I don't go 360 divided by negative 3 gives me negative 120, the period's negative 120. It's not. The period is a positive value. To sketch these, it is important that you be able to sketch these manually and not just using the graphing calculator. So when you want to sketch these manually, what you want to do is adjust for changes in amplitude by considering what the new min and max points would be, and then adjust for the period by dividing the period into 4 parts. So the 4 parts, if we go back to the beginning when I was doing those sketches, the 4 parts would be the start and the end, the x points, and then where the max and the mins are. That's the 4 sections really that we're talking about. How would those adjust if I change this to 180 degrees? Well, this is halfway, so now it would be 90 degrees. This is halfway, it would now be 45. That's how you would adjust it. So if we consider the graph, y equals 4 cos 2x, where x is any value between 0 and 2 pi, what is the amplitude of this graph? Amplitude is 4. And what is the period?
360 degrees.
Divided by, what's the b value? 2. So 360 divided by 2.
Isn't it?
Oh, sorry, radian measure. Let's do that again. So 2 pi divided by 2, which would be pi. The other thing that I need to know is a cosine graph starts at the maximum and then ends at the maximum. So my cosine is going to start at what? What's the maximum for cosine now? 4. It's going to end at 4, which is 1 period, so it's going to end at pi at 4. Which then means it would be up to this maximum point again with the next, because this is an equal distance. What's the minimum value for this graph?
-4.
-4. And when does it hit -4? Halfway in between. So halfway between 0 and pi is when it's going to be at -4. Halfway between pi and 2 pi, it would be at -4. And then in my cosine graph, the x-intercepts are halfway between the min and the max. So if I look, there's my min and my max, halfway in between is going to be like at 1.5. That's where it's going to cross the x-axis. Halfway in between, halfway in between, halfway in between. So now I have my points of where it's going to cross the x-axis. And then I'm going to draw this smooth curve. So it doesn't have to be exact, but I am going to try to draw it as a curve where it's going to go through that x point. And that's what my graph should look like. And if you want later, you can verify that with your calculator. So in the next question, if given an amplitude and a period, can we write the equation? So remember, our equations are in the form of y equals a cos bx, or a sine bx, or a tan bx. So if I look at the first example, I have a sine function that has an amplitude of 2/3 and a period of pi over 6. So an amplitude of 2/3 becomes my a value. And if you remember on the previous page, the period was equal to 2 pi divided by b. Which means if I wanted to find what the value of b is, so if I wanted to work backwards, if I gave you the period, how would you find out b? So if you knew that the period was 180 degrees, how would you determine that b this time would be equal to, not 2, b would be equal to 1/2. No, sorry, b would be equal to 2. How could I use 180 degrees and 360 degrees to get to 2?
Divide 360 by 180.
Yeah. So then the b value is going to be 2 pi divided by the period, which is 2 pi divided by pi over 6. What do I get when I divide these? I get 12. 2 pi divided by pi over 6 becomes multiplied by 6 over pi. Pi's would cancel, 2 times 6. So then my equation becomes y equals 2/3 sine 12x. So see if you can determine the equations for b and c. Okay, cosine function has an amplitude of 3 and a period of 720. So what would be the value of a? 3. What would be the value of b?
1/2.
And how'd you get 1/2?
360 divided by 720.
So then my equation would be y equals
3 cos 1/2x.
Good. Okay, and the last one, a tangent function that has a period of pi over 2. So what would be the value of a? Just be 1. If I'm not told anything else, the amplitude is always 1. What would be the value of b?
4.
Isn't 2?
What's the period of tan normally, Jessica?
Oh,
Right? So pi divided by pi over 2 would give me an answer of 2. So then y would equal tan 2x. Tan is the tricky one because its period is different, and we have to keep that in mind. Okay, if I look at class example number 4. This is a partial graph of a function. We want to state the amplitude and the period. So what is the amplitude?
3.
How'd you get 3?
Well, it goes from positive 3 to negative 3. And then divided by 2.
So max minus min divided by 2 gives me 3. Period. What's the period of this graph? How'd you get pi, Hannah? Okay, it's going from 0 to pi. Each tick mark is a pi over 2, so then I'd have 2 pi over 2, which is pi. So if this is a sine function, y equals a sine bx, what's the value of a? 3. And what's the value of b? 2. 2 pi divided by pi. So then this equation would be 3 sine 2x. Okay, and then the last question. This graph represents the mean the effective tides on mean sea level over a 24-hour period. The graph has an equation, h of t equals a cos b of t, where t is in hours and h is height in meters relative to the mean sea level. Determine the equation of the graph. So what do I need to do in order to determine the value of a? I have to find the amplitude. Max minus min divided by 2. What's the max? What's the min? So 4 minus -4 divided by 2 equals 4. So that's my a value. What do I need to know to calculate my b value? What do I have to look at the graph in order to determine what b is? The period. So in this graph, we're going to be looking at radian mode, because degrees doesn't really make sense. If t is time, radian ends up being a better measurement. Okay? So it's 2 pi divided by the period. What is the period of this graph? 12. It started at 0, and it took 12 hours for it to get back up to, started at its max. Took 12 hours to get back to that maximum point. So b would be 2 pi over 12. Can I simplify that? Pi over 6. So this equation would now be h of t equals a, which is 4, cos pi over 6 t. And if you were to put this into the calculator and use this for your Windows settings, you would get the same graph. So the questions that I want you to work on, for questions 1 to 6, A and C from each. Because again, it's just that review on the transformations, the stretches and such. 7, A and B. 9 and 10. 12. And then 14, 15, and 16. So what we are going to look at for the remainder of the chapter and the week is looking at transforming again. So we're going to look at the next part of transformations, and then we're going to start looking at some realistic, real-life situations where the sinusoidal function comes into place.